drawing on data taken by NASA's Cassini spacecraft as recently as 5 months before its final plunge into Saturn's atmosphere. Scientists have found that the large northern hemisphere seas of the planet's moon, Titan, all lie at the same elevation, just like the Earth's oceans. What this means, says Alex Hayes, a planetary scientist at Cornell University, US, is that these seas are somehow in communication with each other, either via above-ground channels or through subsurface flows that serve to equalize their levels. Unlike Earth's seas, however, they are composed of liquid methane, ethane and nitrogen at an approximate temperature of -180 degrees Celsius. Hayes and his colleagues report their analysis in the journal Geophysical Research Letters. The find was made possible by a companion study, in the same journal, led by Cornell University graduate student Paul Corlees, who stitched together radar mapping data from dozens of flybys over the course of more than a decade to create the most complete possible topographic map of the surface of Titan. It's a difficult process, says Hayes, because each flyby produced a separate dataset focusing on a single noodle-like swath of Titan's surface. It was easy to determine the relative topography along any given one of these strips, but comparing the elevations of features on different strips was more difficult. There are enough strips, however, that they crossed each other, at numerous points during different flybys. That allowed them to compare features, says Hayes. Ultimately, Corlees says, he was able to map about 9% of Titan's surface elevations to a resolution of about 35 meters, and another 25 to 30% at resolutions of about 100 to 200 meters. Although that still leaves big gaps, one area that was extensively covered was the North Polar region, where scientists had discovered large seas, roughly the size of North America's Great Lakes, as well as numerous smaller lakes. One initial finding was that the mapped parts of Titan have about the same altitude range as Australia, about 2,300 meters from lowest point to highest. But more interesting was the fact that the images from the flat, highly reflective surfaces of the seas and lakes gave much stronger signals than the adjoining solid surfaces. The seas are perfectly flat mirrors most of the time. Hayes says, for the seas, we can obtain accuracies on the order of about 30 to 50 centimeters. Using that, Hayes says, it was possible to determine that the seas had the same sea level, except for small differences accounted for by variations in Titan's gravitational field. Similar variations in Earth's gravitational field affect the levels of oceans. This almost certainly means that the seas are linked in some way, presumably via a combination of surface and underground liquid that keeps them at the same level relative to gravity, akin to an earthly water table. But that just applies to the large seas. Titan's smaller lakes can be hundreds of meters higher, with a diversity of elevations. But within drainage basins, Hayes says, the lakes appear to share a common elevation, implying that they too share fluid via groundwater flow, or ground methane in this case, Hayes says. Which means there's a reservoir of liquid we don't see on the surface. Finally, he notes, the small lakes are surrounded by high, steep bluffs. They look like you took a cookie cutter to the surface and made little cutouts, he says. The most likely explanation, he adds, is that the lakes are in collapsed pits where something dissolved out the underlying material, causing it to cave in and create the lake. On Earth, such features, called karst, can be found in limestone deposits such as Australia's Nullarbor Plain, but steep-walled topography around Titan's lakes, sometimes forming 100 meters high rims, is sufficiently different that Hayes and his team aren't sure what caused it. We punted and said we're leaving it to the modelers, he says. Looking at lakes and seas is just one of many ways in which the new Titan topographic map can be used. For example, says Corlees, climate modelers can use it to improve their models of Titan's atmospheric processes. Right now most of the models assume a flat surface, he says, but we know that on Earth, mountains have a huge effect. It can also be used to help understand Titan's internal structure, he explains, including the question of whether it has a subsurface ocean. Francis Nimmo, a planetary scientist at the University of California, Santa Cruz, U.S., who was not a member of either team, says Hayes' study is an example of how much can be learned about a planetary body once one has a good topographical map. For example, he says, in the outer solar system we know that on some worlds big impact basins are deep, while on others, impact basins of similar size are much shallower. Difference arises because some satellites experienced ancient heating events that allowed the ice to flow and the impact basins to fill in, while others didn't, he says. There's no way we could make that kind of analysis without having topographic data, and in this case, the precision of the data is remarkable. Think about that, says Hayes. You're measuring the elevation of a liquid surface on a moon of Saturn using a spacecraft that launched in 1997, to an accuracy of 30 to 50 centimeters. That's phenomenal.